We have the green light. So I would like, first of all, to thank Henry and Krishna for inviting me to this workshop, which is not only beautiful scientifically, but also from a personal perspective. So thank you very much again. I'm going to talk about some ideas that we have about designing codes for some applications that require very high throughput. And the applications we're going to look at deal with high-speed wireless RF links, as well as satellite free space optical links. So the two applications at the first sight may look different, but it turns out that they yield to quite similar constraints in the code design problem. And this work is a joint work with Ayman, Emna, and Balash. So Emna is actually going to get her PhD in a couple of days. So this work is also part of her PhD development. So the presentation goes as follows. I will briefly spend some words on the application scenarios. I will then move to a design of a coding mechanism for this application, and I will show how it can be analyzed in some convenient way, and then I will show some performance that can be achieved. So the applications that we have in mind are, as I mentioned before, of two kinds. The first application deals with what in 6G are called sometimes sub-terahertz communications, which means communications in very high frequency ranges. And in this, let's say, at these frequencies, there is a lot of bandwidth available. So the idea is to move there to enable the transmission that data rates that typically are a little bit out of reach in terrestrial wireless links. So we are talking about something definitely larger than 10 gigabits per second. The second application scenario, which is something on which we are definitely more familiar due to our historical background as a space research center, is a free space optical links, especially in combination with what are called low Earth orbit satellite systems. So satellites that orbit at some 100 kilometers from the surface. So they typically have a visibility time in the order of tens of minutes. So this is the time you see the satellite passing through. And over this pass, the satellites typically experience, in terms of link budget, variation around 20 dBs of signal-to-noise ratio. So you go from very low SNRs to something around 10 dB. So this brings in the need of rate adaptation, which is a key problem in our design. Also here, very high data rates, very high for our domain in optical fiber systems is, of course, something that is much more common. So all these, let's say, applications. So these two applications we have been discussing. They place some requirements on forward error correction. So to be able to sustain these data rates, you need error correction, especially decoders with low complexity. Rate adaptivity is something you need. In the free space optical domain, we have seen why. So you have this visibility time of your satellite, which means that you're going to have very different communication ranges. In sub-terahertz communications, let's say the quality of the link changes also due to the variability of terrestrial wireless links. So by talking with the hardware people in the projects we are involved with in both settings, we found that both scenarios impose similar constraints. In particular, most of the, let's say, systems we are studying in this context are meant to work with low-order modulations. In the coherent case, it can be BPSK, QPSK, or in the non-coherent case can be on-off keying. It is very appealing to have a regular framing structure. By regular framing structure, I'm going to see a picture in a second. What I mean is to have, for instance, periodic frames sync markers. This allows to quickly acquire synchronization with the stream. And of course, to keep the coding simple, we need to look into some efficient coding technique that we know can sustain high throughput decoding architectures. And one example is to go for something LDPC-like. It can be an LDPC, a generalized LDPC, so sparse graph code, possibly with a pipeline decoder architecture. So now the question is, how can we design a low complexity error correcting scheme that fulfills, let's say, these requirements? So before moving on, I was just would like just to highlight in a picture what we are looking for. So we are looking for a coding scheme that allows to multiplex code words in a stream with a periodic start of frame sync marker, which means that the block length of the code is going to be a constant, so n, and possibly we are going to have different rates protecting the different, let's say, parts of the stream. And for the code, what we are looking for is to have a pipeline decoder architecture where basically we enroll iterations over the chip in a way that we can move on with different iterations of belief propagation decoder while getting in the decoder new samples for upcoming, let's say, frames. So the question is how to build something that works in this way. So, so as I mentioned before, so the need of regular framing requires a fixed block length, and the need of working with a pipeline decoder architecture requires to have a let's say, code that operates with a single unique graph for which we can enroll the iterations over the chip. And so what we are looking for is a rate adaptive LDPC code-like scheme with a fixed block length and a single code graph. This rules out, of course, classical techniques that are used to obtain rate adaptivity in many systems, which are shortening, puncturing. So schemes like the 5G codes and many protograph LDPC constructions that are, let's say, well known in literature, they wouldn't work because they would imply a change in the block length. What are, let's say, the possibilities then? Well, one possibility to address this problem is already indicated in the famous paper of Mackay about low-density parity-check codes. So starting more from a joint source and channel coding perspective, Mackay introduced a class of sparse graph codes that sometimes are referred to as Mackay-Neal codes. And if you, let's say, twist a little bit the source coding viewpoint, as we're going to see in a while, you can get a rate adaptive scheme based on a single LDPC code that fulfills all the requirements that we are looking at. So this kind of perspective was actually adopted in a scheme that not only achieves rate adaptability, but mostly achieves shaping gains when combined with high-order modulations by a group of TUM. So at the time, the people working on it were Georg Böcherer, Fabian Steiner, and Patrick Schulte. And this kind of technique, which is known in the optical fiber domain as probabilistic absolute shaping, got a lot of attention in optical fiber. And I believe it is currently employed by a number of real systems. And the reason to use it was not only the shaping gain that was achieved by the approach, but I think a big merit in making this technique adopted in optical fiber was the use of, or the possibility to achieve rate flexibility in an easy way by playing, say, with the original construction of Mackay. So let's see what we can do then with the Mackay construction. So the principle is as follows. So we have a source which is generating bits in a uniform manner. We have a block that is sometimes in literature called the distribution matcher. This acts as an outer code, a nonlinear outer code, which transforms a uniform distributed bit stream into blocks that have a prescribed empirical distribution. So for instance, blocks that have a constant number of ones. This can be a constant composition code, for instance. We have done a linear block code encoder. We go through our communication channel. At the decoder side, we process the constraints of the linear code we use at the transmitter side, and then we undo let's say, the operation that is done by the distribution matcher. So out of this constant composition word, we extract what was the transmitted message. Okay. So what is peculiar in this scheme is the distribution matcher, of course. So this is something that is not very common in existing wireless communication systems. So the distribution matcher, as I said before, is a block that transforms a uniform distribution vector into something that has a biased distribution of zeros and ones. And in the past few years, there has been a lot of research on how to perform this operation efficiently, because in optical fiber, where these kind of techniques are used, these operations have to be performed at several hundred gigabits per second. So we rely on the fact that in the optical community, there is already quite some development of distribution matchers that can work fast. They can be based on enumerative arithmetic coding, shell mapping. There are really many techniques that have been proposed during the past few years. And some key parameters. The length of the message at the output of the distribution matcher, we call it H. The Hamming weight that specifies the empirical distribution of these vectors, we call it E. And this block, in fact, has a rate, so that is less than 1. So it introduces redundancy, and the rate can be very well approximated by picking the binary entropy function evaluated at the fractional Hamming weight of these vectors. So what about the inner code? Well, the inner code is going to be a linear code, and we are going to characterize it through two matrices, H1 and H2. So the relation that defines the code words at the output of this encoder, actually here should be an X, so I apologize. So here we should have X. So X is computed according to this relationship, where in our construction, and in Mackay's construction, H1 and H2 are going to be two sparse binary matrices. So loosely speaking, how can you see this block? Well, you can see this block as a low-density parity-check code encoder, where the LDPC code is specified by a parity-check matrix that is larger than what the code dimensions would imply. You have a first part, which is associated to what sometimes are called the state variable nodes or punctured variable nodes. And the second part that is associated to the code or symbols that you send through the channel. And I think this becomes more clear by looking at a graph we're going to have in a few slides. So what is the overall code rate of the scheme? The overall code rate is going to be the code rate of the outer code, binary entropy function of omega. Omega is the fractional Hamming weight of these vectors, times the rate of the inner code. And you can actually tune the rate of the overall scheme by playing with the empirical distribution of the distribution matcher. So if you change the number of ones in every code word, you can achieve different rates without touching the inner code. And most importantly, without touching the number of bits that are generated by the LDPC code encoder. So let's talk about decoding. So optimal decoding rule is, of course, ML. So if we consider the overall code obtained by concatenating the nonlinear outer code with the inner linear code, we should look for X maximizing the likelihood. Alternatively, we can rewrite this equation by looking for the code word of the inner code that maximizes this likelihood multiplied by a function that filters out all the inner code words that cannot be produced due to the constraints of the outer code. Okay, so This is equivalent to the rule above. A simplified rule, which is mismatched, so it's not maximum likelihood, but it's going to be very practical, is to replace this, let's say, probability that filters out non-valid code words with the product of the marginals of the bits at the output of the distribution matcher. Right. So if I take the product of the marginals, here I'm going to consider actually all coders of the inner code in the decoding, but the ones that are originated by an input with an empirical distribution very different from the one that we set are going to receive a very low probability. And so let's say this term is going to kill the metric, the decoding metric for non-valid inputs. So that's the intuition. So for our LDPC, what this implies, it implies that we're going to have a graph divided in two parts. A first part is dealing with the bits that are not transmitted, which are the ones at the input of the LDPC encoder and are associated to the output of the distribution matcher. What do we know about them? We know only the prior, which is the log of probability of having a 0 over a probability of having a 1 in the sequence. So it depends only on the empirical distribution of the distribution matcher. And for the channel part, we get the channel LLRs. So it's a very flexible encoding mechanism because we know that by changing only the parameter omega, so the parameter of the distribution matcher, we are going to have a scheme that on the encoder side remains unmodified. At the decoder side, the only impact we have is in the strength of the prior. Okay. So the more we shape the input of the encoder, the stronger is going to be the bias. If we pick omega to be 1 alpha, meaning we are allowing input sequences with half zeros and half ones, then the prior is going to be 0. Okay, so now, how to analyze this scheme? Obviously, the overall scheme is nonlinear, which means that there are some complications in the analysis. We cannot use the all-zero code word assumption. There are several things that become a little bit more complicated. But actually, it is possible to turn this problem into an equivalent problem, which is entirely linear. And the idea is that the prior information that we get at our linear LDPC decoder from the a priori distribution of the encoder inputs is equivalent to the observation of the input of the encoder through a binary symmetric channel with an error probability that is equal to the parameter omega we have seen before. Okay, so this can be shown. And at this point, you're dealing with the problem of decoding over two parallel channels. One is a Gaussian channel, another is a binary symmetric channel. The Gaussian channel output affects the right part of the graph that we have seen before, and the binary symmetric channel output affects the left part of this graph. And so keeping now this model in mind, we can do everything we are used to do for the analysis of codes over symmetric channels, linear codes over symmetric channels. So for instance, what we can do is to do a density evolution analysis. So we can construct, for instance, protographs that are optimized for the transmission over a Gaussian channel with a given, let's call it a priori binary symmetric channel parameter. And for example, what we can do is then to optimize the construction of our protograph, so our base metrics, by looking at the iterative decoding threshold. So we have done that using both quantized density evolution as well as exit charts. And exit charts are quite accurate in this setting, but when we started to have a lot of shaping on the information part, then the accuracy of the exit chart approach starts to become a bit questionable. So in our analysis, typically what we do is to use, in our optimization, to use exit charts, since they are very fast, to compute thresholds for rates that are not too low. And when we start to operate in a highly shaped regime for the input of the encoder, we switch to quantized density evolution.
That you
Sorry?
You did that analysis on the mismatch?
On the mismatched, yes. Yeah. And similarly, we can also do an error floor analysis by studying what is the probability of error under maximum likelihood decoding over this surrogate model. And what comes quite clear is that while in a classical setting, what matters is the weighted numerator of the linear code, in this context, to determine the error probability, what it matters is the input-output weighted numerator of this code. So you need to know what is the composition of the information vectors and coders at the output of the encoder to compute what is the error probability under ML. And as just said, the quantity that matters in the union bound now is the input-output weighted numerator. In order to use this information in the code design, we went for an asymptotic analysis of the protograph ensembles that we designed. So we computed a growth rate of the input-output weighted numerator for our protographs. So now, differently from the classical case where you have, let's say, a chart showing the growth rate of the weight distribution of a code, here you have a two-dimensional chart showing what is the 1/n log of the expected number of code words with fractional Hamming weight on the input alpha and fractional Hamming weight on the output beta. And how can you use this to define what is good and what is bad in terms of distance properties? Well, you need to look at the regime where both alpha and beta are small, are close to 0. And in particular, what is important is that when you look in, so this is the same chart as before, looked from the top. So what is dark means it's above 0. What is white means it's below 0. Okay. So what is important is that in this corner, you are below 0, meaning that if you are above 0, you would have an exponentially large number of coders with small input weight and small output weight from the encoder. And that's something that would make the error floor to rise up. So this is an example of a bad ensemble. And you can see clearly that in this region, so small alpha, small beta, we are starting above 0. And of course, colors don't help much, but trust me that here we are positive. So it's very light gray. Okay. So this is an example of a bad ensemble. So now, how do we do the design? We do the design in the following manner. We fix a range of code rates that we want to support, say from 1/10 to 2/3. And we compute iterative decoding thresholds for the base metrics we are trying out. And for each, we sample a number of rates in this range, and we compute what is we call worst case loss. So what is the biggest gap from the Shannon limit that we have at these operating rates with respect to the thresholds we are computing. And we look for protograph-based matrices which minimize this worst case loss. We can do that in an unconstrained manner, meaning that we don't check minimum distance properties, or we can put a verification about the input-output weighted numerator growth rate to filter out ensembles that are bad from a d-mean, or let's say a distance property perspective. So here we have two examples of these matrices. This is obtained by picking those rates as targets for the optimization. So from rate 0.1 to 8.5. What is on the left of the vertical line are the columns associated to the input of the encoder. And what you see on the right are the columns associated to the output of the encoder. So here, if you don't shape the input, so if you enter with a probability 1/2, the code rate that you get is 1/2, right? Because you have 2 columns input, 4 columns output, meaning that the highest rate you can get with this base matrix is going to be 1/2. In this case, it's going to be 2/3. Okay. So let's see the thresholds compared to the Shannon limit as a function of signal-to-noise ratio energy per coder symbol over single-sided noise power spectral density. And what we can see is that with these two base matrices, in both cases, we are able to operate over a wide range of code rates within 1 dB from the Shannon limit.
Sorry?
This is asymptotics. So that's the thresholds. So now to verify that the error floor analysis is working, we designed the code with a bad error floor. That's what we do if we don't want to simulate down to horribly low error rates. And what we can see is that definitely, so these are truncated union bounds using the let's say, analysis I showed before. We see that they predict quite accurately what is going to be the error floor performance for a given code with different shaping parameters, so different rates. So the error floor analysis is confirmed. And here we see an example of two designs done with the length, block length 9,000 bits. So this is the length of our code. We get different code rates by playing with the distribution matcher parameter. And the red curves are obtained for an ensemble that is bad. So it has exponentially large number of low-weight code words. Let's put it this way. And you see that, in fact, this ensemble shows, at least for the lower code rate, starts to show an error floor happening quite soon. And for the other ensemble, we are still running some simulation, unfortunately, but till 10 to the minus 4, 10 to the minus 3, so far we didn't observe any error floor. So concluding, we studied a construction of rate-adaptive LDPC codes based on the Mackay-Neal construction. The analysis is facilitated by looking at the problem from a different perspective, introducing this equivalent linear coding problem. The design can then be based on classical tools because we know how to deal with this linear LDPC design issues. And the results are promising in the sense that we are able to build a single LDPC code based on a protograph construction that is able to perform in the asymptotics within 1 dB from the Shannon limit over a wide range of code rates. So we have an error floor analysis that also helps to address low error probabilities. And yeah, I would like to thank you. This work has been recently submitted, and probably we're going to put it also on archive soon.
Finishing a right on time is exactly 35 minutes. We have time for maybe one or two questions. Yeah, Rudy.
Thanks. Just a quick question. I wonder if maybe the credit should go to Gallagher. Gallagher was the first one who did the matching for asymmetric channels, but using exactly the same idea. So I think,
Okay.
I mean, the idea of matching goes back.
I see. I was actually not aware of that. So.
And then also the buffer and so on. I mean, this is all was done originally in the context of asymmetric channels.
Yes.
But it's the same thing. But maybe my question was more, so you could of course also just add constraints that you switch off, right? I mean, you can still have the same block length, but simply take the number of checks that you have to be variable, right? Would that not also work?
But that would mean changing the encoder then for.
Switch off some of the, I mean, in hardware that shouldn't be so difficult to do.
Yeah, but suppose, for instance, that I mean, there is a work like that by Sam Dolinar. But if you do that, then the encoder is going to be modified. So not the decoder, but the encoder, because you're basically changing the parity-check matrix structure. And unless you, I mean, there might be a way to do that, but I don't know if it is so trivial.
I think you all had a question. You raised a hand before you. So.
My question is about the distribution matcher. It's not ideal. It's some algorithm that
Yes.
you check the effect of these non-idealities on performance.
Yes. So simulations are done with a real distribution matcher, which is based on inverse arithmetic coding, and yeah, they are consistent with the analysis.
I was just going to make a comment about that one way that you can have a variety of rates but maintain the same parity-check matrix, and do what Rudy was saying is that you can combine rows basically take two parity checks and make them into a single parity checks. And you can design a family of rate compatible codes that have the same block length.
I don't think they would be rate compatible. I think they would be rate adaptive. Yeah.
Rate adaptive.
Rate adaptive, exactly. Yeah. But I believe that as well in this case you would have a different encoder than if you change the rate. At least, I mean, it's not obvious to me that you can keep the encoder structure unmodified if you change the subspace of the parity check matrix, right?
Okay, let's thank Gianluigi once more. We're going to take a 20-minute coffee break and we'll be back here at 10:50. Thank you.